Good afternoon from Barcelona, and welcome to a new Rhino webinar. Today I'm here with my colleague Pedro Cortés. He's an architect and computational designer, and we're starting a new series of webinars by expert users in different fields. It's a pleasure to have today with us David León for this first edition. Actually, David is a former colleague with us. He has worked for McNeel Europe for a couple of years. So he knows the company, our business philosophy, our tools very, very well. And David is currently the head of computational design at IaaC. This is the Institute of Advanced Architecture in Catalonia, where he directs the Master in Advanced Computation for Advanced Architecture, MaCAD. And he's also a guest faculty in the MPDA Masters program of the UPC. That's the University Polytechnica of Catalonia. Today, David will speak about the process of teaching Rhino development tools within the context of his master's program at IaaC, and what's the different applications of these tools in the stage of academia, and the benefit of learning, again, these development tools for professionals in the AEC market, in the architectural, engineering, and construction market. The webinar will cover interoperability, cloud computing, and machine learning with practical examples and a quick demo. So David will start with a presentation, then a quick demo will follow. And during the last 15 minutes, there will be time for any questions or feedback you might have. So please feel free to use the chat on the right panel on your screen. And yeah, both Pedro and me will collect all your questions or your comments, and then we will pass this to David. So David, many thanks for being here, and it's your time now.
Thank you, Carlos. Thank you, Pedro, for the invitation. It's really nice to see you guys again. Carlos, it's been a while since I see you also. This time, maybe we were meeting there in the quarters of the McNeel Europe office a few months ago already. And now it's also nice to be in the other side of the webinars also to explain a little bit about what we do in IaaC, about what we do specifically in the context of the masters. And I guess for the benefit of time, I might just start sharing my presentation and maybe we just carry on. Welcome everyone too. It's kind of funny not to see you in the screen because this is being live stream, I think. Hold on, I'm just looking for my presentation here. Okay, great. Just to confirm, you guys see my screen, right? Pedro, Carlos, can you guys can see my screen at the moment, no?
Yes.
Okay, great. So maybe we can just get this started. Well, I've been kindly invited by Carlos and Pedro to start this webinar series again, which one that I'm very fun about, that I've been also following as first as a McNeel employee and also as a viewer afterwards. And it's a real delight to be here again with you guys. This time to talk a little bit about what it is that motivates us to teach Rhino development tools for AEC. Right. So I think Carlos has already painted a broad picture about my profile. Mainly just to complement, I'm an architect. I'm a trained architect with focus in the research of development computational tools for architecture, construction, and engineering industry. I'm currently heading the computational design department of the Advanced Architecture group in AEC. Also directing the Masters in Advanced Computation for architecture and design, which is the one that I'm going to be talking about. And well, not just to spend too much time on me. I was also part of the McNeel team almost a year ago, and I'm happy to be here again with you guys, as I said, from the other side of the screen. I want to start my talk by painting a broad context of the motivation behind what we why we teach these tools, and there are some bigger questions, of course, involved, like one particular important one that states that asks, why do architects actually need to learn these computational tools in the first place? And I think it all boils down to the role of the architect in the first place. And this, just to, not to with any intention to capitulate any more than just a broad stroke of the role of the architect throughout the times. It has all to do with representation. It has all to do with the following of specific instructions, right? It has all to do with geometry, with drafting, with making our ideas visible and communicatable to others in the design process. And this process has become, of course, ever more complex since we started building in the first place. And it's, of course, tightly related to the tools that we have had at hand since the beginning of this process. First, by when we talk about hand drafting, the incorporation of technical tools to gain more precision in our drawings, to communicate those drawings faster, perhaps establishing certain conventions that now we take, as architects, sometimes take for granted. And finally, through the inevitable incorporation of computation in the design process, these tools or these facilities have gotten just mainstreamed, and somehow it feels from the architectural point of view that in some senses it has exploded in so many directions, because of course computation now touches so many aspects of the architectural trade. But it's setting aside the I guess most common use or most common notion of computational design in architecture, which is basically this picture that we have of complexity in complex forms, and basically transforming our mind ideas into volumetric complexity. I think there lies a more complex, a more rich dialogue in the evolution of this process of conveying our ideas in between architects, in between a team, or between the designer and the final user, right? So I guess along the lines of time, starting from hand drawing, going through technical drawing, and through the incorporation of computer-aided design by the use of technical drawing in our screens, and there probably more plastic or more freeform types of designs, all the way up to what we now call computational design. What we have gained technically can be described as an enhancement in precision, an enhancement in the complexity, or basically allowing us more complexity within our design process. But more than that, I think it's a matter of also being able to represent or to incorporate in our buildings, in our design, so many different dimensions beyond the 3D dimensions that we know. That means dimensions like time, dimensions like property, and these dimensions, once we have included these dimensions into the design process, we start to establish already a dialogue in between what we are used to meddle with when we, as architects and designers in the first place, which is basically geometry and notions of space and spatial quality and everything that we're currently still being taught in architectural schools. But also, it's tightly related. It's tightly related now to the management of data, because data is what gets in a very basic way a very naive way to say it. Data is what it gets attached to this geometrical process in order to enhance the dimensions in which we can look at this at the projects currently. So these questions that we have now in the screen are actually some of the questions that we consider to be relevant nowadays that we should ask ourselves, not only from the architectural professions point of view, but also from the academic point of view, because there is certainly a gap, or sometimes a long stretch in the process of learning from what we learn as architects in our universities to what sometimes is expected from the AEC trade, and that maybe can be an overstatement, but for sure it can be validated for some of the results that we've gotten in the launch, or basically in the goal of setting out this educational process that we launched a couple of years ago with MaCAD. So the questions like how can we explore different options of the design process to evaluate this design, which is basically immediately related to parametric design, and whether complex shapes can actually give us different or more performative outputs, or more performative buildings as a result of the design process. And also what kind of properties, right? Or what kind of data should our models contain nowadays in order to improve such performance, often with the goal of sustainability, or with building our buildings with a wider scope, or a wider lens, and a more critical view of the impact that our buildings have nowadays. So this chapter is tightly related to what we call building performance. Then there's also the fact that, as I was saying in the beginning, different software make different properties, no? And this is also widely polarized by the huge amount of specialization that now take place in the building process. So not only as architects we have different options to draw our drawings or to convey our ideas, but we also have to communicate to other agents in the design process, which in turn are using different software and different computational tools. So how to collaborate basically in this wilderness of different languages of communication and specialization. How to attach properties to these geometries, basically. This is related to the aspect of BIM, right? Where our models are ever growing in information. Hence the building information modeling name. And this information gets attached to what in principle is basically what we just geometries, and that's what we start with when we usually model. And then how to collaborate with the different specialists managing different data, but not only that, how to collaborate with the end users of our designs, how to make them participants in the design process, how to collect feedback from the users and from everyone that is involved in this design process. And that all has to do with the tools that we use for design. And then there's another aspect, which is, of course, quite trendy right now, which has to do with a more sophisticated approach to design, but not only design, but every other process that has to do with computation, which has to do with data, and big data, and the available data that we can use to inform our building design process, which helps us put our projects into context, but also as designers and as end users, it would also help us to unveil certain aspects of our intentions, say aspects that often we're not aware, because of course the dimensions in which we we face or tackle our design challenges are not encompassing all of the dimensions that the building usually has to face in reality. So that has a lot to do with computation, and altogether these three chapters, which somehow we have isolated, and all challenge currently the role of the architect. And I leave this as a huge question because at the moment, I think the scope of this conversation is not as much controversial as large, but it is, of course, to me, is still an open question in terms of what the role of the architect is currently. However, those questions still stand, and in order for us to tackle those questions or to address those issues, here in IaaC, a year, actually 2 years, almost 2 years already ago, we set out to launch a new master in Advanced Computation for Architecture and Design, in which a master in which basically we would aim to tackle these questions and fill in the gaps that professionals face nowadays in addressing these issues, right? So I'm going to try to explain how we deal with these development tools, as the tools that I'm going to be talking about in a minute. How do we use these tools to tackle these questions that I posed in the first place, and all through different examples of student projects that we have developed in these three separate modules. And at the end of, hopefully, if there's still enough time, I will just make a little demo of a specific aspect that we consider is key to making this work, which is basically interoperability. But for now, I would like to start by telling you a little bit about how the master works. And here, I guess this is a little bit of shameless promotion also, but the aim is basically to paint a broad picture of how do we structure the education that has to fit in one master, which is basically 1 year of education, in order to impart so much technical knowledge and so much, of course, background, theory background and conceptual thinking behind everything that this encompasses. So we have the master has 3 separate modules, which can be taken as 3 separate postgraduates. And each of the modules tackles each of the scopes that I was mentioning there in the beginning. First module that runs from October to December has to do with computation for environmental and structural design. And the second module, which is the one that we're currently at, tackles building information modeling and smart construction. And the third module tackles artificial intelligence and architecture. And all 3 of those are composed of technical seminars that we have to go through, that the students go through, and a theoretical class that to sustain all of the conceptual knowledge that goes behind the use of these tools. And then finally, and probably most importantly, one studio course, which aims to propose with the tools that are learned, make practical proposals in terms of projects with the tools that are learned in the masters. So I'm starting with the first module, which has to do with environmental and structural optimization. We start with one seminar which is called Complex Forming, in which it's basically not only not an introduction to Grasshopper, because we do expect some previous Grasshopper knowledge, but actually it's a broad course in terms of the study and the research of form finding tools for parametrical design, right? So in this seminar, which is basically based on Conqueror 2, there's a broader exploration of different form finding strategies in order to attain, of course, certain parametrical knowledge that our students use and set out as a base from this module on for the rest of the masters. We have another seminar which has deals with structural optimization, and then and this one's based on Caramba. Of course, I have to make an emphasis that teaching these seminars is not teaching the tools themselves, but it's actually teaching the tools in a context. No, so they're taught by an amazing an amazing group of faculties which are expert on these tools, but also expert on the use of and the practical use of these tools, both in research as in current practice. So in a way, it's not a tutorial. It's basically, it comes with a lot of background knowledge and a lot of notions on the background of structural optimization. So it's cannot be considered just a plugin tutorial. And finally, towards the goal of performance analysis and optimization, there's the seminar of environmental analysis, which has to do with more with the use of the Ladybug suite in order to analyze our buildings for structural performance and of course figure out different strategies in which we can actually enhance this performance towards more sustainable building. For all of the modules, there's a studio and a theory course, and I want to start by showing you a little bit of the work that our amazing students do in the studio. And this is a project by Natalia Voinova, Sajin Davas, and Harsha from the first year of MaCAD, which basically takes a research approach into an analysis of the city of Moscow, right? And start by setting out by finding out the site in which to set out a building, and of course through a research approach, start finding contextual parameters which should inform the building design process. Right? There's of course a deep analysis of the use of performance tools such as radiation, radiance, solar analysis, environmental analysis, but more importantly, there's of course the response from the parametric building strategies towards these analysis in order to find the most suitable option in the end. As I said, the studio, of course, encompasses not only the design, a design strategy, but several methods of conceptual analysis that our students go through in order to have critical thinking about each of the proposals that the computer in the end provides. So different variants of through generative optimization or through different methods of form finding, different variants of the buildings are explored, and finally, of course, the building enters in a loop of proposal analysis in which, of course, at the end, the designer has the control, has the basically the decision in which where to stop or which to finally bake a final iteration in some sense. This analysis is taken further, of course, through afterwards through structural optimization as well, right? So varying certain parameters, always with materiality in mind, in order to find most performative options of structure. In this case, we're talking about the building skin, right? But how does that also affect the different constituents of the building, in order to result in of course less or more viable options by the analysis of different parameters that are recollected from the parametric design process. And finally, of course, we always aim that our projects become architectural, and they should have architectural features, always escaping the conceptual stage as much as possible. And of course, given the fact that all of this that you see for each module is only developed within the scope of 3 months, which is in my mind nothing short of amazing, and it never ceases to impress me in terms of what the students can achieve in this period of time. Secondly, moving on to the second module, which addresses more the idea notion of BIM and smart construction. We tackle. I think it's fair to say that we don't tackle this is not a BIM course. It's not a course in which you would learn Revit or learn how to become a BIM manager in a way, but it is a course in which you would tackle different the key aspects of the BIM paradigm nowadays, such as interoperability through rhino.inside, for instance, in the integrated modeling seminar, in this case, rhino.inside Revit, with the aim of transferring or establishing a conversation in between a software that is able to modulate freely like Rhino and generate complex parametrical designs in Grasshopper, and another software which is aimed to for drafting and documentation, and finally, of course, the production of federated models that are becoming more and more standard in AEC practice nowadays. Another aspect that the module touches is intercollaboration through the collaborative workflows seminar. In this case, taught by in collaboration with the team of Speco, which basically aims to tackle the challenge of how to intercollaborate within a team freely and in real time through more like I would say more like a development paradigm, right? And finally, a seminar called Cloud-Based Data Management, which through Hops and rhino.compute, another Rhino technology that we teach in this module, aims to push the boundaries of our models beyond Rhino into the web, so that we can share the models that we have, but not only the models, but the different options or the different performances of the model that we are able to display in the web, in a platform which is widely accessible by other people, creating apps and configurators from our models. This is something that our students are currently doing right now in this current module that we're going into. This involves a lot of sometimes some scripting, some JavaScript learning, some web development learning, and of course, it's an intense but highly rewarding experience in the end. I want to show a little bit of what the outcome was for that in the studio last year, which is a project by Hesham Shauki, who is now working with us in IaaC as well, Herman Bodenbender and Marisa Ritzuan, who I hope are listening there in the background. These guys were so involved in the project that they actually put themselves into a suit on a lunar suit. And here, I guess it's fair for me to explain also that there's a lunar agenda in the design in this module, because in order to find an excuse for nuanced projects and intercollaboration, and of course put our students in a situation where they would have to face completely non-traditional, non-canonical projects, and actually face the challenge of taking those to a more canonical approach, like documenting in Revit, for example. So the project starts as usual very conceptually by proposing a lunar habitat composed of different modules. And these guys, of course, explore many different variations. Now getting a bit more intense in the use of plugins. In this case, I think they were using Wasp to create stochastic variations of the project. But of course, never leaving aside the actual physical and fabricational constraints of what it takes to building a moon. So in the end, their projects are highly involved, not only in terms of design, but of course in detailing of these design modules in the moon, and in the exploration of different iterations of the design process, always with the goal of achieving a certain performance goal in mind. In this case, you can see the phase of construction in the moon was also taken into account, so it became quite kind of a realistic project. And here, a bit of the computational workflow that is established for one such project like the one that you guys are seeing here. So there's a stochastic aggregation by WASP. There's a structural analysis verification by Caramba. There's basically intercollaboration and export and interoperability to rhino.inside and Speckle. So mainly in the end, our students push these projects also as configurators in the web, where you can see here, let me put this a bit faster. You can see here already, more or less in a nutshell, how can they allow users to explore different variations of the project by running grasshopper definitions in a website. And not only that, but also the structural and analysis of walkability, for example, finding shortest path, or structural verifications of each of the projects, then actually exporting these all of the different options for analysis into a web sheet, right? Always creating amazing visualization visualizations that are helpful to inform the architect and the user about the different options that we have at hand. And finally, taking this to pushing this to Revit also, and through Speckle for collaboration, for intercollaboration. This is in the end result is a set of plans produced in Revit that are specifications for the project, as this would actually be an actual fabrication project. Such specifications that actually contain these properties and data that we've been talking about. The different dimensions of the project that these geometries contain in schedules and tables that are, I would say, impressive for the fact of being stamped as a sci-fi project in the first place, right? This is actually taken to reality. Then you see configurations of the project, and of course, always a really nice visualization of the project itself. In the broader scope, this was one among many groups that settled the moon in this module. And there's of course intercollaboration between the different projects that have populated the moon in this studio, and they have an ongoing negotiation of how to place their projects and how to colonize the moon, how to propose a massing site with their colony through Speckle and through talking among themselves. There's a web app for this project, but I'm gonna have to skip it for the sake of going on, for the sake of time and for the sake of explaining this other project. Also by Germán, but also, in this case with Amar, Felipe, and Alexander, which is called Urban Voids. This project, sorry if I skip this part, this project is part of the Artificial Intelligence in Architecture module, which basically tackles issues of data encoding, generative planning, and geometrical optimization. This project, I think it's going to exemplify all of the aspects that the module tackles, and basically aims to provide a data-driven approach to analyze the hidden opportunities behind the urban fabric, right? So our students set out to collect and clean a database, which often they produce through Python libraries like NetworkX, find different scores within a topological optimization techniques such as shutter spats and so on and so forth, and then analyze through machine learning, in this case, k-mean clustering techniques, how they can actually make sense of this data and cluster different features of the projects that are not only the two-dimensional aspects that you see in the map, right? So this, in the end, all of this is brought to the web for an app that I was showing in the end of the presentation. And of course, it's an interactive app where the user can actually navigate and see the proposal, right? So this, according to Grasshopper and Urbano, basically, this is the data that it's collected in a more flat scenario, right? So the project poses the question of how can we actually make the process more efficient and reliable. And then, of course, the different projects of the studio tackle different aspects and also use different Python libraries, but they're all encapsulated in the framework of machine learning through Python. In this case, using NetworkX and GeoPandas to put this into the map, information into the map as topological optimization processes. The project, there's proposed scoring for such an analysis, and of course there's always an evaluation or a benchmarking at hand in order to compare whatever they set out to do and whatever the result actually was from what they proposed, right? So they worked with a huge billion data sets collected from Melbourne, Australia, using OSM, OpenStreetMaps, using Python. And then basically through the machine learning model, through k-means clustering in this case, they start to find basically different analysis in which they can provide information for the end users in the app that they develop. So I'm going to pass this a little bit faster because I see that the time has run a little bit on us. But of course, I think you can see here all of the dimensions that are explored and all of the different type of analysis that are featured in this project in order to finally come up with an objective result out of all of the information that is collected in the end, right? And more than that, I think I want to save a little time here for the demo too before and for the discussion. But I do want to show you these that we're always pushing our projects to become something real, something outside of the the shell of academia or the shell of the comfortable zone of basically our realm of investigation, and always through the creation of applications that can be explored and actually used by different users in the different users that actually might benefit from this information. So here, for instance, you can see actually I'm going to backtrack a little bit of the link here. This is the app that was created in the end, which is a site which you can actually go there and check on your own. And it has, of course, an explanation of the project. Here are the project participants, and of course our senior studio faculty, Angelos, along with Leah, that run the studio. But more importantly than that, you can point these tools to different map scenarios in which you can actually see the result, right? The clustering of the area selected here, and how through different aspects that are analyzed, you can get a quantifiable collection of how that area would perform in these different features that are being analyzed here, right? This is all being displayed live. I guess we could actually point this information to many other places, but for the, just to show, these guys I think have created a brilliant application which you can not only explore but actually use if you're in such a place. I'm a bit sorry that I had to run through this last part, but of course I'll tell you much more about this, and there's a lot more information about what we do in their seminars in our MaCAD site, right? And of course our applications are always open, and so if you're more interested about these tools, about these seminars, or possibly joining our masters, you can go to the site and of course explore a lot of what's been going on with different articles and different publications that the students have been involved with. I wanted to leave a little bit of time for the technical also, because just to show you a tiny bit of what our students are usually involved with in terms of, in this case, bringing a widely known platform for artificial intelligence and collaboration like Google Colab into Rhino through hubs, which is basically our vessel in the whole masters to bring all sorts of computation from different places into Rhino, into Grasshopper, into a familiar territory for our students. So I will start basically by showing you these. I hope I don't have to run. Yeah, that's great. This Colab notebook, right, which is basically the base in which our students operate in terms of machine learning for the last module, right? And in this little notebook that I have here, that I can that you're seeing, I have actually started by installing certain dependencies, right? This is something that you would only run once, and basically installing the GHub server, right? And something called Flask ngrok. Now, this is a very interesting dependency, because it actually not only brings Flask, but it also brings ngrok, which is a service that allows you to open a local port in whichever machine that you're running, so that you can communicate to the external world through the web. And in this case, everything that's being run in a Google Notebook, for those of you more machine learning or computational savvy, it's basically hosted in a machine somewhere, in a Google server somewhere. And basically that means that you're running these computations somewhere in a Google server, no? But in order to open a door, or maybe in more technically speaking, create a tunnel from that place to your own local Rhino compute, you need to go through this process of, actually using ngrok, which is an amazing facility. So for those of you who don't know it, I highly recommend it, not only for this context, but as a real easy way to communicate from local to the internet. Now, what I'm doing here is just basically importing the usual suspect libraries here, Flask, ngrok, the GHub server, NumPy, and Rhino 3DM. For those of you more involved in machine learning, of course, Matplot for plotting. In this case, I have a base setup. I'm also using scikit-learn to create a dummy data set of points, right, which you can create with the make blocks function of scikit-learn. And I'm just going to use this mainly to create a data set of points to operate with, right? So I can create 50, I can create 100 points here, and then I'm just using matplots to plot them so that you can see the distribution of these points in a plot. Now, the interesting thing about using all of these libraries is that similar to the workflow that the folks at McNeel has already shown us in which you can actually communicate from Visual Studio to Rhino, you can actually use ngrok and Flask to create a server here in Google Colab to communicate from this site to Rhino. And this is what I want to show you very quickly, because I guess time is of the essence. I'm just going to widen my screen a little bit more. I don't know if you can see.
Don't worry, you still have time, David.
Oh yeah, great. When I finish this, I'll ask you, Carlos, if I can still continue or if I should stop. Right. So as for now, as I said, I have this base code. Right. In here, I'm running nothing else but just basically creating the basic setup that has been described by Esan or Steve in one of the posts in the McNeel forum. That maybe hopefully I can point to. I should have pointed this to you in a link, but I can actually point to you that afterwards. I guess a lot of you guys already know that in any case. Yeah, I mean, running this server, I mean, setting up this definition by actually decorating it with the hops component decorator here is basically providing, like we're always doing, attaching additional information to this function so that hops can recognize it as a grasshopper, as a hops component, right? So in this case, I just called it test. This is going to be my endpoint. I just named it test here because it's just going to be a test. And I'm going to collect the string from grasshopper here, right, through the end parameter. And I'm going to run it through this function. And then afterwards, I'm going to return it to grasshopper after just by formatting this text that I have here, right? So there's no real magic here. Everything has been done already by you guys in McNeel. The only thing that I'm doing here now is just basically, I'm doing this somewhere in Frankfurt, I guess, in the server, and I'm going to relate it to my local computer here, right? So I hope everything runs correctly now that I run the server, and it does. Seems. This takes a long. This initial line takes a long period to run, so I preset this. I pre-run this before, but now that the app is running, you can see it's basically constantly running, and you actually get an address here that you can use to communicate from the Colab repo from the Colab notebook to your own local compute. Now, here, for example. I'm not going to even bother explaining hops at this point, but I assume that there's some hops knowledge already. But for those of you who don't know, hops is just is basically a vehicle which uses rhino.compute as a grasshopper component in a way to link compute to grasshopper. So if I just use my public address here, that's been created by ngrok. And I actually add the endpoint that I just created, which is basically a test. I should have, yeah, as you see, I am actually getting a communication from Grasshopper to Colab. Every time that I make a request, you'll see it here in the panel. And for example, if I just type my name in this input that I have defined in hops, as you can see here, name, right? You'll see that hops is basically solving this in Python, right? There's a request being made to this endpoint in the Flask server, and then the server is returning whatever this function made, right? So in this case, yeah, welcome to the MaCAD server, right? That's it. Can I have 5 more minutes, Carlos?
Yes, sure.
All right. I just want to stop my app at this point, and I just want to show you how easy it is then after to benefit from the libraries that you have here already installed by the Colab environment quite nicely to bring them into hops, right? So I have created this definition already predefined, but I could actually create another definition here, right? And this is something that I also had prepared, which is basically, I'm going to do this in 2 steps. I want to first create a Python definition here that converts NumPy arrays to points, because what I have here is a NumPy array of dummy plots, and I want to create actually Rhino 3DM points from those. So it's just a very simple definition that takes a NumPy array and returns a point list in Rhino, right? So I'm going to run that to save it in the Colab environment, and then I can actually just add another endpoint, right? That says basically get points, that is defining the definition to run. That is defining a definition that runs this previous definition that converts the NumPy arrays that I have previously defined up here in X to points in Rhino. And I'm going to send those points from Colab to Rhino, right? So if I just run this, if I run this, I have actually created this endpoint. You see, this one actually has no inputs, right? I'm just recycling the function that I had up here. In this case, my endpoint is going to be called get points, right? And then I'm going to have to rerun my app, of course, so that this is actually taken into account. And again, I take this this little URL. I hit the get point endpoints, and hopefully, yeah, as you can see, I get my plotted points, the same plotted points that I have here, which I think they have been. I mean, the coordinates are different, are rotated, but as you can see, the same plot that I have there on the matplotlib plot, I now have in Rhino. I was planning to do a little bit more, but I think this covers it. I mean, this is just a little taste of the base of what our students have to go through to run really complicated and really complex machine learning definitions that they run in Colab, collecting the huge data set that they process with pandas and process with NumPy, then with Scikit or TensorFlow and other libraries in order to bring those stuff to Rhino, and also collect inputs from Rhino and bring it back. But I hope this was just kind of like a taste of what we do in MaCAD. All geekiness aside, I think this is a really useful workflow if you have anything running in Colab that you want to bring to Rhino.
Excellent, David. Many thanks.
Thank you, Carlos.
I hope I hope the audience enjoyed the presentation as much as we did. Just one question, one guy or woman, sorry, I don't, because of the name, I don't know it, asks if there are any prerequisites of computer science to join the MaCAD.
No, there isn't any. The only prerequisite to join MaCAD is to have some Grasshopper knowledge. That is going to be really beneficial because it's the base tool that we use for the whole masters. But everything, I mean, both on the BIM module, both on the web development part, you're basically, you taught from start, and also in the machine learning part, you also taught from start in terms of Python. Of course, it's beneficial to know a little bit if you know already.
Nice. There have been some comments and many thanks from many different people that some of them I'm sure you know because they are your students or your colleagues, but very few questions. I don't know, Pedro, if you have any question for David.
Yes, I have one question for you. First of all, thank you very much for your presentation. I think that it has offered an incredible overview about what challenge we tackle as designers these days. But well, you have explained all these tools that are currently in the design process, new workflows, different languages of coding, Python, JavaScript, and collaboration are more and more common these days with developers, architects, engineers. So the question is the designer evolving to a more complex or more specialized professional?
This is the question, I think, Pedro. I mean, this is something that I have to say I'm really curious about, because I think there's no doubt that the designer has to, up their game in terms of technical knowledge, ever and ever. No, so every year we impart new tools, and the designer has to learn new tools, and the demands both in every aspect for practicing architecture nowadays is more complex in the terms of, for example, having to use software as a Revit or different other software for rendering, for instance. And if you add to that computational design and introduction to programming and scripting, then the amount of things that you need to learn as an architectural student becomes huge. So I think there's kind of this is the question, whether is the architect supposed to learn all of these tools, or is there room for a new role in between that provides for the architect such tools without the architect having to have this knowledge, which is basically the computational designer. No? So you can see already in many specialized offices in AEC that they have specialized computational design groups, which are in charge of creating tools for the rest of the team, without the team having to really know all of these tools, but they just need to they need to know the basics of Grasshopper, or maybe through the tools like Hops or the Grasshopper player. They only need to run the Grasshopper definition without having to set up the definitions. So it's, to me, still, the question in a real incognita in terms of, how much does the architect needs to learn to catch up versus, how much specialized one has to get as an architect, or choose to be a computational designer as an option. No? Yeah.
Because from your experience as an academic, how different is the learning curve for a student since these new tools has appeared in the design process?
I think it's not easy to learn. To learn programming and to learn different languages, it's not easy to begin with, but it's a steep learning curve. But I think once you're past a certain point, everything becomes much easier, because setting aside all of the different languages that you could learn for programming, and considering, for example, Grasshopper as a kind of as a introductory drug to programming through Visual Scripting, I think Grasshopper makes a really good job of changing the mindset of architects that are used to drafting towards thinking about architecture as data and geometry and data and processes, which is more towards what programmers do.
Yeah. So, because at the end, we as an architect or designers, we want to show our work in some way. Do you have a preferred platform or tool to visualize your projects or your experiments?
You mean type rendering, such as rendering?
Or rendering, I don't know, or a platform like a web app, for example.
Yeah, I think I'm more. I think I have stepped aside a little bit from that aspect of architecture, and more I'm inclined in stripping the shiny parts of architecture and more displaying the data parts, the performative parts of architecture. So in that sense, I think by creating web tools, you're creating your own visualization of your projects, but the designer is also empowered to show different layers of the projects that are not usually visible in renders, for example, like performative gradients or structural information, or any type of information, data information that you want to attach to your project. I hope that answers your question.
Yeah, sure. Absolutely.
Just two more comments and questions from the chat. Constantina Angelotou asks if you know if these methodologies are already used in the actual industry, but German Otto Bodenbender already answers that yes, they are. At least he can speak from a personal experience, and we see this all the time with some of our customers, of our key accounts. There is one more question. It's a very broad, it could bring us hours and hours of discussion. So I let you answer this in 1 minute by Thomas Kopinski. Where do you think AI is heading in architecture in the next few years?
Where do I think AI is heading? It's a great unknown. If I rather answer where I want it to be heading, I think, and that is as kind of as a sidekick of the designer, and not as a designer itself. That's my very personal, take on this. I guess as a really powerful aid for the designer to take decisions. I hope that's the end route.
Nice. Very nice and short answer, but yeah, I guess it's what we all expect from AI, not to do the things, creative things and so on, but to help us as another tool and bring us more possibilities. There is also Kemal Arda Alkin from Turkey, and he knows how to navigate this knowledge of computational design, but he says he cannot find a specialist job in the industry in Turkey right now. If there is any kind of advice we can give him about professional practices.
That's a tough one. I think it's very contextual. It's a very contextualized, but I hope that this trade can also benefit from the globalization that we now live in, a way that I see more and more remote opening positions that you can apply to.
True.
You agree, Carlos, also with this?
Yeah. I mean, we see on LinkedIn all the time new job positions, and some of them require to move to the place where the AEC practice is, but some of them are remote. So I would keep an eye to LinkedIn, and also contact us sometimes. There are some companies that contact us directly looking for someone with these skills. And thanks to you, from Tomasz Kopinski, from Peter Donders, from Andrés Velasco Muro, from Kemal Ardalkin, from Shamila Zubairi. It was a pleasure. We ran out of time, but I think it was worth. And we wish you all the best at the IaaC and at the UPC.
Thanks, Carlos.
And hope to meet you soon and have some beers. We live in the same city, but during the last times we had to.
Yeah, we have to reconnect.
Everything becomes better. And to the audience, many thanks for watching this webinar. It has been recorded, so in case you missed the beginning of the webinar, just it's on this same link where you will be able to watch the entire webinar. Thanks also, Pedro, for your contribution and organization. And have a nice day, everyone.
Thank you, guys. Thank you, Carlos.
Thank you, Flohio.
Thank you, everyone.
Have a nice day.
To the MaCAD students that contributed to all of this project. Thanks, you guys.
Bye.
Okay.